Hello students and welcome to Mr. Goddard's review on electrostatics and circuits. Without further ado, let's start going through this. So, first up, essential formulas. So, these are the AP formulas. The first one, this is Coulomb's law, where you can see that the magnitude of the force between two charges is equal to Coulomb's constant, which is on the back of your formula chart, times the value of the charges. Now that's going to be measured in coulombs, divided by the square of the distance between them. Obviously, we've mentioned over and over again, though, that this formula closely resembles the Newton's gravitational formula. Then we have the definition of current, namely that current is equal to the change in charge divided by the change in time, so the number of charges that pass a given point during a given time frame. The resistance formula, the resistance of a wire is equal to the resistivity times the length of that wire divided by the cross-sectional area. Of course, Ohm's law, we've got that the current is equal to, now this is the current through a resistor, is equal to the voltage drop, or the change in voltage across that resistor, divided by that resistor's resistance. The power that is dissipated through an element, or maybe through a light bulb, maybe through a resistor, is equal to the current that goes through that times the voltage drop, or the change in voltage through that element. Then the equivalent resistance of, if you have a bunch of resistors in series, then you can simplify that by summing up all of their individual resistances. So R1 plus R2 plus R3. This is the way that it has the formula on your formula chart, because this sigma means sum, sum each resistance, each resistor's resistance. Now, if your resistors are in parallel, then it's 1 over that equivalent resistance, or they're going to have Rp for resistors in parallel, is equal to the summation of the reciprocals. So it's sort of a two-step process. You have to say 1 over R1 plus 1 over R2 plus 1 over R3. That's equal to 1 over the equivalent resistance, so then you have to take the reciprocal of both sides to find what that R sub P is equal to. Alright, just a very brief review of what charge is. We sort of started off talking as if you had no idea what a charge was. We noticed, there's two types of charges, positive and negative. Like charges repel, opposite charges attract. The force between those is a long-range force. Neutral objects have an equal mixture of positive and negative charge. Whenever you execute the rubbing process here, then that's going to be transferring charge, negative charges pretty much every time. And charge is conserved. It cannot be created or destroyed. That's a huge one right there. Conservation law is kind of sneaking in there at the end, but that is a very, very important principle. We talked about insulators and conductors. Not a whole lot to say. Discharging is by removing the charge from an object. Also, this concept called charge polarization, and that is that you can have a slight separation of positive and negative charges even in a neutral object when a charged object is brought near. So for instance, if you have something that's all positive, even though this sphere right here is maybe plastic, or maybe it's made out of like styrofoam or even paper, even though it's not a conductor, the charges will separate a little bit, and that can create a net force on that object, especially if it's light enough, that will then attract it to that charged object. We did this in class with the comb and the little pieces of paper and whatnot. So this is called charge polarization, and it is a very real phenomenon. We saw it happen multiple times. All right, the whole point here of this sort of diagram is so that you've got electrons and protons. The electrons are negatively charged, and charge is an inherent property of both electrons and the protons. Some of the other things, there's no other sources of charge. That's basically the only two sources of charge. If we say an object is charged, that means that it has some unequal number of protons, electrons, either more protons than electrons or vice versa. And then objects gain a positive charge not by gaining protons. You're never really going to grab some more protons onto an object, at least in the situations that we're talking about, but instead you're going to be losing electrons, or if it has a negative charge, then obviously it's gained electrons. And the reason for that is that protons are very tightly bound to that nucleus. Electrons are bound more loosely. Charge is represented by the symbol Q, and we measure it with coulombs. The fundamental charge of one proton or one electron, we use E, the lowercase little cursive e, for the fundamental charge. That's equal to 1.6 times 10 to the negative 19th coulombs. So if you have one proton, then that's plus E. One electron, that'd be negative E. And one of the things that we notice is that you can only have multiples, whole number, or integer, positive integer multiples of this charge value, because you cannot have half a proton or 2/3 of a proton, or 5/8 of an electron or something like that. So it has to be 1 times this, 2 times this charge, 3 times this charge. Those are the only possible values of charge that you can have. Okay, and this is just sort of a summary statement on that. Looking a little bit closer on Coulomb's law, we saw that at the very beginning. We noticed that if we were to graph it, we would notice that as the force increases, as the radius or the distance between the two charges increases, the force decreases. We can also see that just by looking at the formula here. Since the r squared is in the denominator, obviously that's inversely proportional to the force. Another thing to remember is Newton's third law, that is that the force on one object that is charged due to another is equal to the force on the second object due to the first. So for every force, there's a sort of an opposite force counterbalancing that. All right, so this is just talking about the direction. Like charges repel, opposite charges attract. Coulomb's law is like any other force. You can add them all up to find the net force. And K, we didn't mention that earlier, maybe it's way at the top there, 8.99 times 10 to the 9th. And there's the units. Of course, all that's on your formula chart. All right, electric potential is the potential for creating electric potential energy. There's a formula. It's not on your formula chart. You really don't need to know that. However, the way that we do measure potential energy is joules per coulomb, which is the volt. But what we tend to do is we tend to measure the potential difference. That is, what's the difference in potential energy at this terminal than this terminal. So we're not really interested so much as what's the potential just at this point itself. We're like, well, if all the charges from this terminal on the battery were going to move through here down to that, then this other terminal, then what would be the change in the potential energy there? And so you can see we've got a 9-volt battery. This multimeter, voltmeter setting here looks like it's 9.66, so it's a little over 9 volts. Great. And so use a voltmeter. I think here at the end we're going to look at that a little bit more in detail. Talking about current, several big picture things. First, current is the motion of charges through a material. They flow like water in a stream or in a pipe, which is why we call the movement of electrons or charges, we call it current. Electrons must have a closed path or a closed circuit, otherwise they won't move. So if you've got some sort of break, they can't make that jump, so they'll just all stay there. They actually will travel if you have a closed loop, and you can see the light, the lamp there turns on. Electrons that are moving will bump into the atoms and heat up the wire. So we have here a battery. You can see the charges, the electrons here are leaving through the wire. They're hitting, this resembles a wire or maybe some sort of resistor. These larger spheres here are the molecules. As the electrons bump into them, then these charges move back and forth faster and faster and faster. And the temperature goes from cold to about lukewarm here, but they're moving around faster. And you can see here we have an electron sort of bumping into all of these as it's in this electric field from the negative terminal to the positive terminal. Other things we notice, the current going into a resistor equals the current going out of the resistor. This is just an application of the principle of conservation of charge. So that said, otherwise, charges are neither created nor destroyed. So current is always the same in a wire. All right, so if the charges are leaving here, going through the battery, going over to this plate, they will not be destroyed if they, even if they cause this light bulb to light up. The light bulb will light up because of those electrons' interactions with the molecules in the actual light bulb here. So the idea is the current before the light bulb is equal to the current afterwards. We saw this with little pinwheels. Even though it's causing the pinwheel to spin as these charges are moving through, then even it's still spinning, but there's still the same number of electrons going into this element as leaving it. This just sort of says that same thing. Current is the same at all points in a current carrying wire. Another application of that is if you have a junction, you've got some place where the current splits, maybe say like in a parallel circuit, that the current that's going in will equal all the current that is going out. Or if you have maybe two inputs like this current plus this current together will equal that current, because current is a measure of charge and charge cannot be created or destroyed. Something else we talked about, the current through a wire depends on the voltage across it, that's the potential difference, and the resistance of a wire, how much fight it puts up. Then there was this whole thing, the current is the flow of positive charges, and we were like, what the heck, if we really had a positive terminal here and a negative terminal here, we all know that the electrons, which will freely move, will travel through this wire and go up here to the positive terminal. However, the direction that we choose to draw the current arrows is the direction that positive charges would flow, if positive charges were able to flow. Of course, we all know they can't. It's really electrons traveling, but this is the reason, or this is how we do it. And the reason is, if we really want to go through it, it's because the current arrows is also the direction of the electric field. And if you remember, the electric field shows what a positive charge would do. So therefore, if you have a bunch of positives here, then the electric field will be pointing away from that positive charge, that positive plate, and then towards the negative plate. So anyway, that's our understanding of current, and so the application of this is that we're always going to draw our current arrows out of the positive terminal of a battery. Okay, current, as I mentioned at the very top here, is the number of charges that pass through a given cross section in a given time period. So that's change in charge, or the number of charges that pass in a given period of time, so delta Q or delta T. The units for current are amps, which stand for a coulomb per second. Batteries, well, at one level, we said the batteries use charge ferries to move the electrons from the positive terminal to the negative terminal. In actual fact, it's actually chemical reactions are the charge ferries. And a dead battery is where those chemicals have been exhausted. Those reactions can no longer occur. So if we think about this in terms of positive charges, you can think of the battery as a charge escalator, where there's positive charges down here and they bring up, are brought up here to the top, and then they will flow out of the battery through whatever elements we have here in the circuit, and then back to the negative side. Another thing we noticed about batteries is that if you have multiple batteries stacked from the positive terminal here to on the negative, then the positive here to the negative, then the voltage, that potential difference, is going to add. So we could say down here at the bottom, if this was 0, then at this point right here we would have 1.5 volts more than down there. And since that's connected to here, then whatever the voltage is here, then we have 1.5 more than that point right here, and we have 1.5 more than that point up here. So the idea is that we can say 1.5 plus 1.5 plus 1.5, and that will tell us the total voltage from the very bottom here, the very negative terminal, to the very top. Resistance is a measure of how hard it is to pass charges through a wire. You can see here they're going through no problem. Here it's a little bit more difficult, a lot more resistance. You can see if you measure over here on our sort of sliding scale of resistance, we have low resistance, about 0.27 ohms, and here we have a lot of resistance, 0.87, although that's really not a whole lot of resistance. you could have thousands or even millions of ohms. But for this example, there you go. The resistance in the wire, you could put this just in terms of Ohm's law. We actually measure resistance in ohms in honor of Mr. Ohm. That formula, once more, resistance is rho L over A. Where, just a little bit more in depth here, resistivity characterizes the properties, the chemical, well, I'd say it's the electrical properties of a resistor, which are determined by the chemical makeup inside that resistor. The toaster. Resistivity of a metal increases when the temperature increases. The idea is you're sending more charges through that wire, then it's the wire, the molecules in there are going to start moving around even more, and then it's going to be more difficult to send charges through that wire. So as a result, as the temperature increases, the resistivity actually increases as well. So it makes it harder to send current through there, and that's a good thing. Otherwise, if the resistivity decreased, then you'd be able to send even more charges through, and then your toaster would melt the wires. Like I said, resistivity is based on the molecular composition. We can see a nice little table of the various materials and their resistivities. This was just the light bulb and kind of what was going on inside the light bulb, the filament, and you've got two terminals here, one right there and the other one down there. When you have resistors in series, what the battery would see, so to speak, would be just the sum of those. If they're in parallel, then it's 1 over that, and 1 over the equivalent resistance is 1 over the reciprocals. And something I didn't mention earlier, the reason for this what happens is that the equivalent resistance of a parallel circuit is always smaller. It's less resistance than either one of these. It's, if this is a 100 ohms and this is 200 ohms, then the resistance of both those together is less than 100 ohms. And the reason why we discussed is there's more lanes of traffic. If you think of these charges, some of them are going to go through here, but then others will go through here. Even though it's a little bit tougher, some of them will still go through there, and as a result, you end up with more current going through here. Ohm's law is that the current is equal to the voltage drop divided by the resistance, and you can go through all sorts of thoughts. As the voltage goes up, the current goes up. Voltage goes down, current goes down. Resistance goes up, current goes down, because they're inversely related, and so on. Ohm's law, get this, only applies to ohmic devices. So an ohmic device is some material in which Ohm's law holds. So how's that for circular reasoning? The idea is that if the voltage drop and the current are linear, then boom, you have an Ohm's law sort of situation. If they're not, then we would call that nonomic, or nonohomic. It's non-ohmic devices if it's not a linear relationship right there. Energy and power, we can think of the energy leaving the battery as the energy through the resistor. Here's our power formula. You can, using Ohm's law, change that P equals I delta V into like I squared R or delta V squared over R. It just depends on which two of the three are given: voltage, current, and resistance. Then we talked about circuit diagrams and all the different components that you could have. We're really just concerned with junctions, switches, bulbs, batteries, wires, resistors, not capacitors in this course. Alright, you've got to have a closed circuit, the current going in to a junction, current going out. We already mentioned that. One thing I haven't mentioned yet, Kirchhoff's loop law, that is that if you pick any point and add up the change in voltage across every component, every item there, then that sum is going to equal 0. That's a logical conclusion. If you end where you begin, then you're not going to have any change in potential energy. So we can look at that just in terms of a battery and resistor. Basically, the delta V, that is the change in voltage across the battery, is equal to the voltage drop across the resistor. Series and parallel circuits. One of the things that's interesting is that the two bulbs in series, because the same current is going through both of them, if they happen to be the same resistance, then the brightness is based on the brightness of each bulb is based on the current. So the same current is going through each one of them, so they're going to both have the same brightness. If we have a parallel circuit and both of those bulbs happen to be the same resistance value, then this is also interesting. The current that leaves the battery will split. Some of it will go down this branch, the other part of it will go down this branch, and if those bulbs have equal resistance, now this is the only case, is if they're totally equal, then that current will get split exactly in half. And so half of the current that leaves the battery will go through this branch, the other half will go through that branch. Consequently, both these bulbs get the same current, and therefore they'd be the same brightness. So it's kind of an interesting situation where if your bulbs have the same resistance, then these two bulbs have the same brightness because the same current's going through them, and these two bulbs have the same brightness because they have the same current going through them. However, these bulbs over here would not necessarily have the same brightness as these bulbs over here. That would depend on the resistance. If anything, if let's say all of these were 100 ohms, then this battery would see 200 ohm resistance. This battery would see only a 50 and so actually more current would go through these, and these bulbs will be brighter. Lots of other ways we can analyze that. All right, so we already talked about the equivalent resistance multiple times. Not a whole lot to say, just that sort of example you can see here. This has arrows discussing what I just talked about. The current leaving the battery splits. Some of it will go through here and some of it will go through this resistor over here. All right, the equivalent of several resistors in parallel is always less than any single resistor in the group. Measuring voltage and current, you're going to use an ammeter and a voltmeter. An ammeter, you have to rip up the circuit and put it in series with it, and we did that in the lab. So a voltmeter, however, you can just sort of get those two voltage probes and attach them there at either end, so you can measure this in parallel, so to speak. You can measure the voltage. More complex circuits, just sort of a little shortcut. If you have two identical resistors in series, then the equivalent resistance is 2 times that resistance value. If they're identical and in parallel, then it's that resistance value to cut in half. Okay, and then we talked about how to simplify some more complex circuits, and basically you just sort of work your way from the very end here. You've got 2 in parallel, and you can reduce that 10 and 10 to that'd be a 5. And then so therefore this is a 5 and that's a 5, so those two together would be a 10. So this battery would just see a 10 ohm resistor. You can calculate the current that goes through there, and then you can split it up and do all sorts of fun stuff like we talked about. Okay, so that's everything with electrostatics and current. Thanks for watching. Feel free to go back through here and look at any particular slide you need. Good luck on your test.